If the star at the center of our solar system vanished this second, the first several minutes on the surface would remain ordinary. We sit roughly 150 million kilometers away from the sun. Even traveling at the universal speed limit of 299,792 kilometers per second, the final photons emitted by the star require 8 minutes and 20 seconds to reach our eyes. This delay applies to more than just light. Albert Einstein's general theory of relativity dictates that gravity also propagates at speed c. The sun's gravitational grip on Earth remains intact until the last of its light arrives. During this brief window, Earth continues its usual elliptical orbit around a point in space that no longer contains any mass. The perception of physical reality on the surface is synchronized to the time it takes for information to traverse the vacuum. At the 8-minute 20-second mark, the causal horizon finally reaches us. The sky turns black, and the gravitational tether instantly severs. Earth is now a rogue object. It breaks its circular orbit and travels in a straight line, heading into the interstellar medium at 67,000 miles per hour. This darkness expands outward through the solar system. Because Jupiter is much farther from the sun, it remains visible in the terrestrial sky for nearly an hour as the final light reflected from its atmosphere completes its trip back to our eyes. Within the first 24 hours, photosynthesis stops. Without the constant 1,361 watts per square meter normally provided by the sun, Earth begins radiating its stored thermal energy into the vacuum. The planet is now a cooling thermal battery, isolated in a space resting just above absolute zero. The Stefan-Boltzmann law dictates that an object's power output is proportional to its temperature. As Earth cools, it sheds energy faster while it is warm and more slowly as its temperature drops. Within a month, the average surface temperature falls low enough to freeze the top layers of the oceans. This surface ice acts as a thermal insulator. While the surface remains frozen, the water at the bottom stays liquid for hundreds of thousands of years, protected from the cold of the vacuum. After 1 year, the surface reaches -100 degrees Fahrenheit. Water vapor and carbon dioxide condense and fall as snow. As the temperature approaches 33 Kelvin, oxygen and nitrogen liquefy and freeze, accumulating as solid air ice. The Earth's atmosphere is a state of gas sustained by constant solar irradiance. Survival on the surface is a mathematical impossibility. Any remaining human presence must relocate to subterranean habitats deep within the crust. Geologically active regions like Iceland offer a template for survival. Here, civilization could harvest the 44 terawatts of geothermal heat flowing from the interior. Sustaining closed-loop agriculture and extracting oxygen requires high energy density. Nuclear fission reactors would be sited at least 300 meters underground to maintain thermal stability. Deep-sea extremophiles are insulated from this catastrophe. Living around hydrothermal vents, they rely on chemical energy and would persist completely unaware of the sun's absence. The only life forms capable of outliving the solar system are those that never required its founding star in the first place. Earth is now an interstellar wanderer, drifting through the dark expanses of the Milky Way. It is mathematically possible for a rogue planet to be captured by a new host star, which would trigger a violent planetary thaw as frozen gases sublimate back into an atmosphere. Without such a capture, the internal heat engine eventually fails. Over several billion years, the radioactive isotopes in the mantle finish decaying, and the core solidifies. When the internal heat flux ceases, the deep-sea vents grow cold. Earth's temperature finally matches the 2.7 Kelvin background of the universe. The history of life on Earth is a phenomenon enabled by the energy of a star.